Right, another practice here for US 18239 element 4. This time we've actually got three resistors that are identical, but most importantly to note that the parallel resistors are the same value. So let's see if this can be any quicker and shorter to actually solve this problem. So we're already pretty good at this. Hopefully by now we know that we've got to basically get a series circuit to begin with, which consists of this resistor here plus, or in series with, this large resistor here, which in reality is two parallel resistors. So we're going to have RT equals 820, that's this one there, plus whatever this is. Now let's actually work it out. R parallel equals, and there's a couple of ways you can do it. I'm going to do the I'll do the proper way, and you may opt to do the shorter way, which is the product divided by the sum. 820 to the power of negative 1 plus 820 to the power of negative 1. Now that's actually 2 times 820 to the power of negative 1, but if your maths is good, which equals, now have a look at this. This will see if the number means anything to you that we get when we do this here. Bracket, wake up sir, wake up. 1 plus 820 to the power of negative 1 negative 1 equals 410 ohms. Now take a close look. 820, two 820s in parallel, and we get 410 ohms. 410 is in fact half of 820. So we rule, just to be aware of, that when you've got two resistors in parallel, if they are the same value, the effective resistance is half of that value that you had in parallel. It only works when they're the same value. The rest of the time it'll be something different, and it'll actually be something greater than the lowest value resistor of the two. Greater than? Yes, less than, but getting closer to it. Sorry, greater than half of it. Forget that. Let's just move on. The point is, half of it, half of that resistor, which is in parallel, is what you'll get. So that equals, oh, do we need a calculator for that? Hopefully not. It's 1200, whoops, and 30. 1230 ohms. That's me doing head maths. If I've stuffed up, then put in a comment if it allows for it, which it probably will be blocked by now. Oh, by the way, that should be there. That's all G's, homies. Right, okay, now, currents. I1, that is the current going through this resistor here. Or it is also the current going through the battery. So generally I think it's easiest to look at a full circuit picture here. You know, what does the battery see if you put probes looking basically across this? So the whole circuit, oh no, sorry, it gets this. Gee, am not doing very well here. What is the total circuit current is what I'm saying here. It's the total circuit current because it's what the battery gets through it, and therefore we're going to go, if we use our Ohm's law again, V equals I times R. Okay, I equals V over R. Now if we go for the whole circuit here, because we don't have enough information here for what the voltage is across that one yet, so let's just go the whole circuit, which equals 9 divided by total circuit resistance 1230 ohms, which equals, and let's just plug that through, that equals, oh, now that's milliamps, which would be fine, but again I think just playing it really careful at this stage, I'd shift engineering, get it to zeros up there, so that's your raw value there, so that equals 0.007, get to 3 significant figures there, amps. Okay, now here's where we've already found one thing where it's a whole lot easier, where they're the same. You can just halve that to find the effective resistance to get this. However, there's more easy things here. You see I1, here's I1 coming in here, and some of I1 goes this way to I2, and some of it goes to I3, and I2 plus I3 will equal I1. Okay. However, well, let's have a think. Normally it's about the two resistor values here, if there's a lower resistor value, more current will go through that one because it blocks it less than the other one, than the high resistor. However, they are the same. So what is obviously going to happen to the current in terms of how it splits when they're the same? Of course, sorry, just bashed the stand holding the camera here. Well, in my excitement, well, of course, you end up with half of this one, of half of I1. So it's actually legit if you've got that sort of circuit to say I2 equals I1 divided by 2 or over 2, okay, because that's intuition, that's perfectly legitimate. So I've already got that value divided by 2 equals, and of course we're going to get that down into its raw form. You can put it in milliamps if you're happy enough. In fact, it would be fine because of course that's what the multimeter will tell you. So maybe in this case it would have been better just to have kept it at milliamps. Don't forget to do the rounding there on those numbers. Yeah, because when you measure it, and I'm not going to show you how to measure this one, you've already got a video on that. Whoops, hang on, where are we going? You could have actually put 7.32 milliamps in here. 3.66 milliamps. If you're comfortable with it, it is better to do it this way. However, if you don't trust yourself to mess up when you're converting, just play it safe. Now, I3, again, real easy. Remember, they split evenly. So I3 equals, the easiest way you can say that, I3 must be also equal to I2. Okay, because they get the same amount each. So therefore, 0.00366 amps, which equals 3.66 milliamps, or whichever way. You can just have this answer if you like. I'm just showing off, you know. Right, now, voltage. This now becomes pretty damn easy too, because we've got VR. We know that V equals I times R. So VR1 equals I times I1 times R1. Okay, we've got all those values now, which equals I1, which is this one up here. Sorry, just get the whole thing on the screen for you. 0, and this is where the milliamps, if you put the milliamp value in here without changing it, that's where there's problems. So maybe you want to, sorry, I should have put this over here, but this is where, you know, it's important that you just get that raw number in, or you divide this by 1,000. Maybe just put the raw number in to play it safe. Times resistance was 820, was it not? Okay, let's just, I'm going to get that back to where it was, okay, and then times 820, or you can just put in the values here, start again, but you know. Oh, equals 6, sheesh. That's a rather, after all those big long crazy numbers, we've got a very boring looking straight number here. I suppose we should put it to, you know, to some significant figures, 3, but you're cool, not hugely important. You can just put 6 if you like. Now, VR2 must equal I2 times R2. Okay, because voltage across R2, I2 times R2. Okay, which equals, now in fact, jeepers, well, we already know that that is actually equal to half the current that we just did times 820. So in fact, it must equal, I don't even need to do the calculator for this, this must equal 3 volts, mustn't it? I just 0.3.00. It must equal 3 volts, just through rationale. Okay, and then VR3, well hang on, well you could do the whole thing equals I3 times R3. However, the other thing you say, well it is in parallel with this, therefore it must be the same as VR2. So that equals this. So equals, let's just take it way out to here. So they're all lined up, 3.00 volts. Now remember, the other thing remember is going around a loop, the voltage drops must add up to the voltage, the power supply. So we go round, we go 9 minus 6 is 3, and we have 3 here. We go round, 9 minus 6 minus 3, that makes 0 again as well. That's great. Even if we go around this loop, parallel, one of them will be, because we go plus minus, if we go around a loop, one's negative to positive, one's positive to negative, plus 3 minus 3, plus 3 minus 3 equals 0. So even that works if we get down to the raw basics of it. So there you go. That was nice and easy, wasn't it? A lot easier when you've got the same values here, and even having the same value here as that creates a few patterns, as you can see, to make it nice and simple. Okay, thank you.